That is. Let's see. How do I press the forward button? Which one? The one on the right. There we go. Okay. If you go back and look at the Lunar Soil Grain Size Catalog, which was published back in the mid-90s, and you go to Lunar Apollo 11 Soil 10084, you will find one measurement for that soil, when in fact many measurements have been made for that soil, and these are the values for the median size of all those measurements that were made. So I think there's something a little funny about this, and I thought it was worth investigating. And I also had at my disposal a new instrument that could measure a much more higher resolution values for these. So I'm showing these histograms here for this new laser diffraction measurement that we can use now. These earlier measurements were not really amenable to making histograms, because if you only have 5 data points, then your histogram will change a lot depending upon where you decide to set your bins. So it was reasonable for them to just do cumulative curves and medians, and from that we're going to work forward. My question is, what's happening that makes all of these results so different from each other? And the answer is there's a lot of different techniques that are used. Dry sieving, wet sieving, and more recently, laser diffraction. In the dry sieving, the finds are underreported, and my co-chair, Christine, talked about the fact that the small grains will adhere to the larger grains. When you're doing dry sieving, those tiny grains have no motivation to go through the sieve and into the pan. So you end up with a situation where you don't really get the number of fine particles that are really in the soil. You don't measure them. And then if you do wet sieving, also fines can be underreported, but for a different reason. The smallest particles will either dissolve or they will clump up. So then you get some really strange things happening, and I'm going to go into that a little bit more. The traditional fluids that were used for wet sieving are water and freon, and both of them react with water. They can cause clumping and dissolution. When I started doing laser diffraction, I was doing it the way the manufacturer told me to, which was to use water as a carrier fluid. And essentially, I found out that I had the same problem. Some of the particles were dissolving, some were agglomerating. I was ending up with bimodal particle distributions. And finally, I switched over to isopropanol as a carrier, and those problems went away. Another source of confusion is that the Lunar Soils Grain Size Catalog only reported particle size measurements based on the 1 centimeter to 1 micron size distribution, when in fact the people who got the soils to measure only had from 1 millimeter to 1 micron or so. The 1 millimeter to 1 centimeter soil particles were not included. So there's this big disagreement about what's a soil. Do we define it at the 1 centimeter mark or not? And a lot of corrections were trying to be made to account for that. And this is exactly what happened here. They take their measurements on the less than 1 millimeter soil fraction. They get information from the curator on what the larger particles were, and then they kind of try to fit all in together into one thing. And the results that you get from doing that is you got from Mike Duke a median of 60 microns. John Graff reinterpreted his data, got about 61.6 for the median, and a mean of 85 microns. That's a graphic mean, which is a little different from a regular arithmetic mean, but that's terribly complicated, and I'm not going to bore you with it. But in any case, the less than 1 millimeter data was not presented in the John Graff catalog of Lunar Soil Grain Size catalog, only the 1 centimeter to 1 millimeter. So anytime you're looking at a lunar soil grain size measurement, please be careful and understand what it is you're looking at. What size range? Are they including the big particles or just the little particles? Are they using some other kind of measurement? You don't really know. But here's what I did find out. Lunar soil grains will clump in water. This is Apollo 16 soil 62241. I just put that on a glass slide, and put a drop of water on it, and you see that all the particles have accumulated around the edge. They're very hydrophobic. I'd used the same soil and a drop of isopropanol, and I did not see that. I saw very excellent dispersion. Freon is even worse. I did another test because I just wanted to make sure what I was seeing was right. I took the same amount of soil, more or less. This is an Apollo 14 soil. This is a jar with some Freon in it. This jar has isopropanol, and this jar has water. You can see that the water has a lot of very small particles, very well segregated. You can see that the Freon has fewer larger particles, and that the isopropanol has a very broadly distributed area. You don't see clumping in this isopropanol sample the way you do in the other two. So this is serious. Clumping. Here's another example. This is from a microscope slide, the edge of the water droplet. You see all of these soils have gone right to the edge. This is where the water is. This is where it was dry. And they're just stopping there. And then here is the Freon. You see that after you remove the Freon fluid from the jar, you still have these little packed on things that are like cement. They're very hard to remove. So we did another study to see if something else was happening. This is a dissolution study. We tried water and we tried isopropanol using an Apollo 14 soil. Now, here is the control. That means what happened when there was no soil in the water. It had this much silicon, this much calcium, aluminum, and so on. Now, when we put the lunar soil in the water and left it for a few days, we had a much larger amount of silicon, calcium, a little bit more aluminum, a lot more magnesium, and roughly the same in these others. So you see there was a lot of material that was dissolved in the water. We did the same thing with isopropanol. Here's our control, which actually seems to have more silicon than the one that we put the lunar soil in. There's obviously nothing is dissolving in this case. So here are some of the results that we've gotten, and the squares are sieve data for this Apollo 11 soil set. The open circles are the measurements that we made in water, and the closed circles are the measurements that we made with isopropanol. And you can see in every case that the isopropanol measurements show typically smaller values. The water measurements and the sieve measurements are kind of grouped together. Apollo 14, same thing. You see that the laser diffraction measurements with isopropanol come out smaller in every case. So, when sample sizes are small, the problem gets even worse. This was demonstrated very well by a paper written by King. He got 3 lunar soil samples. One of them was 14 grams. The other 2 were about 1.5 grams apiece. On the 14-gram sample, he got a mean of 52 microns. On the other 2, he got means of 63 and 69 microns. So he got a larger mean when he had a smaller sample size. And this is actually a much larger allocation than most of the people got for doing sieves, for doing particle size measurements. They were usually about 1/4 gram. And when we do the laser diffraction measurements, we only use about 0.1 gram. So we can actually do a much better job with a lot less material. One other point to make is that you'll see median and you'll see mean and you'll see graphic mean reported for all of these soils. The median is the one you should be using. Folk and Ward disputed this and thought everyone should use graphic mean, but median is not affected so much by the problems that you have by the large grains on either end of the distribution, and it is more consistent in all of the lunar soil measurements that I've looked at when I compare them to the medians. And the median should always be reported, in my humble opinion, whether you do or do not include a mean. So Hapke was another person who measured the Apollo 11 soils, and he came up with a very small number. He said that the median was about 30 microns. And because of that, his data was excluded from the Lunar soil grain size catalog because it didn't fit with the rest of the numbers. But actually, his value was pretty close to correct in the sense that it agrees with my numbers. Okay, so we've measured about 38 lunar soils with laser diffraction, and we've found that laser diffraction with isopropanol is the best method for the present. Thank you.
Yeah, very good, Bonnie. Being the last author on this, I wasn't sure, but I'll say a few things. There's a lot of corporate memory that comes out here. The fact is that Apollo 11, Apollo 12, Apollo 14, and 15, we considered less than 1 millimeter to be the soil. We call that the fines. And then with Apollo 16, we got really smart with all these things. The second number became the site and all that. And we had all these numbers which were 0, meant unsieved, 1, size 1 was less than a millimeter, 2 was 2 to 4 millimeters, 3 was 4 to 10 millimeters, and then 5 was a rock. So we defined soil as less than 1 centimeter. Okay. Now this was sort of an arbitrary thing. We got away from talking about things like we have on Earth, and we were making up our own nomenclature there. The second thing is that one of the major things on LESAP that we had with allocations was the fact that we had the Brazil nut effect with lunar soils, and that we had sample boxes or sample vials that samples were taken from, and they had done a part of a separation themselves. So to have a really, really good sample, you have to use a whole lot and make sure you don't get any kind of aliquot that has a size differentiation built into it. And I think that one last thing is that isopropanol is good. What about other dispersants? I mean, they have dispersants that are specifically set up for that type of reason that you're talking about. So
I agree, and I haven't looked at all the possibilities for dispersants. I started using isopropanol because it was relatively inexpensive and abundant, and I was on a tight budget. But I agree, there's probably a lot of other things you could use, but please don't use water.